Let's go. So graphing f of x equal to x minus 5 cubed plus 2. So this is going to look like the parent graph x cubed. And x cubed looks like this. It's not my favorite to draw, but not a very good drawing of x cubed, but you get the idea, I hope. So all we're doing is we're moving that 5 to the right and 2 down. So specifically, I've looked at where the origin, right, because the origin is one of the points on this graph, even though I have not drawn it well at all. I'm just thinking about where the origin is moving. So it's moving 5 to the right, 1, 2, 3, 4, 5, and 2 down. So there's where the origin is going to be. And it's going to kind of, so typically when I think about graphing this one, which I know, again, not my best, let me try drawing it one more time. I often think about actually 3 points. The points -1, 1, 0, 0, and 1, 1. How it kind of does this kind of deal like that. So I'm thinking, well, this one's going to have those points also move 5 to the right and 2 down. So I'm going to have where 0, 0 move to, and then I'm going to have 1 over and 1 up. So that's 5, -2. That's 6, -1. And then also 1 left and 1 down. So these points are, I don't want to label them because I'm going to try and draw the graph. But this is the point 4, -3, and then 5, -2, and then 6, -1. And then it's going to have this kind of shape. That looks, I've drawn worse. And if you really wanted to, you could go 1 over. If you plug in 7, 7 minus 5 is 2. 2 cubed is 8. 8 minus 2 is 6. So you get the point. So this would be, you don't have to label these points. I'm just labeling them so you can see what they are. 6, -1, that's 5, -2, and that's 4, -3. But specifically, right, we went right by 5, down 2. Those were the shifts that we did, right? We subtracted 5 on the inside of the function, so we moved 5 to the right, and we subtracted 2 on the outside, so we moved 2 down. Questions about this one? I will mention, not that we're going to find them, but this graph has domain everything, right? X can be anything. Also has range everything, right? You get all the y values down to -infinity, all the x values up to +infinity. There is an x-intercept right here. We're not going to find it, but you could find it by setting y equal to 0. There's also a y-intercept way down here. You can find it by setting x equal to 0. The y-intercept would be 0 minus 5 cubed, which is -125, minus 2. So it'd be super negative, -127. But there is both an x and a y-intercept. Here's another graph. F of x equal to the negative of the absolute value of x minus 2. So the x minus 2 is going to take your normal absolute value graph and shift it 2 to the right. So you can, if you want to, draw like a bunch of graphs that show the shifts. Like, so here's the parent graph, absolute value of x. And then I'm going to shift it 2 to the right. So there's the absolute value of x minus 2. And then the negative outside is going to flip it vertically across the x-axis. Because I'm changing the y values to be the opposite of what they were. So it's going to flip it down, and I'm going to have that. That's my graph of the negative of the absolute value of x minus 2. Shifted 1, 2 to the right and flipped it over. If we care to mention it, we can talk about how the domain is everything. The range is all the non-positive numbers. So everything from -infinity up to 0. So where the range is y is less than or equal to 0. There is an x-intercept. It's +2. There is a y-intercept. It's -2. But there's not a lot else to say about this graph, right? We're really just talking about how these shifts and reflections happen. Yeah, I should say that because it is important. So I have an extra example in here that I want to do. it's not going to, oh, actually I have one more example here that I want to do, and then an extra example. But what I want to say is, in addition to kind of having these shifts and reflections, there is usually an order that you want to do them in so that things don't get messed up, for lack of a better word. And the order is, you want to do the horizontal things first. You want to do a horizontal, oh gosh, I'm going to say it wrong. You always want to do, you want to do the horizontal shift, then the horizontal reflection, then the vertical reflection, then the vertical shift. I know it's kind of like a lot, but that's how it works. And I'll definitely model this in the next examples. The most confusing one, actually, let's not say that yet. Let's do one more and then we'll talk about the most confusing combination, in my opinion. At least it always confuses me. So let's do this one. Let's graph f of x equal to the square root of negative x plus 3. So that's going to take our normal square root graph. The negative inside is going to flip it horizontally. So, right, here's our parent, square root of x. And then we're going to deal with the negative on the inside, which is going to flip it horizontally across the y-axis. So here is square root of negative x. Again, you don't need to draw either of these intermediate graphs. I'm just kind of showing you my thought process from how we get to the parent to this. And then we're going to add 3, which is going to shift it up 3. So we're going to get our final graph of, sorry, I should have drawn more on the left here. 1, 2, 3. Just moving that point up like that. So it's going to be like that. So there's our final result. I don't need you to be much more precise than this. It really is all right. I want you to know that this point here is the point 0, 3. And that's all I really need. If you wanted to, you could plot another point and say, okay, well, if x is -1, then -1 is 1, the square root of 1 is 1, 1 plus 3 is 4. So that one would be -4. If you really were just felt like you had to put one more point on there, that would probably be the next point I would graph. But that's kind of it, right? We flipped it, we shifted it up, and we're done. Yeah, go ahead, Nicole.
So yeah, for like the graphs and stuff, we don't need to plot specific points. We just need to show you that we know how the graph looks.
Well, so that's a good question. I would say generally yes, when we're talking about shifts and reflections. I would say, and I'll be very clear on an exam, if I'm asking you to graph a line or a parabola, I will almost definitely be asking you for a line where the x and y intercepts are, for a parabola where the x and y intercepts and the vertex are. So for these kinds of things, if you're just shifting and reflecting, I don't care so much about extra points, except for like maybe where the kind of original point that's important goes. But for graphs that we've already talked about, like lines and parabolas, I am going to ask for more information about them.
Okay, thank you.
Welcome. But yeah, the point of this section is more just to have an idea of how these transformations really work. I mean, there's one type of combination of transformation that I think is a bit challenging, and it's the following one. It's f of x equal to the square root of -x plus 2, where we have a horizontal reflection or flip and a horizontal shift. So, right, that's going to give us a reflection horizontally. Right, everything's horizontal here because everything is happening inside the function, right? We're doing all this stuff before we actually take the square root. And this is going to be a horizontal shift. And here's what I want to say. The way that I have decided, so let me just say one more thing. It's just not your question. What I've decided about this is you always want to do the horizontal shift before you do the reflection. So we always do, so the order we do things in is always from the inside out. So we're going to do horizontal shift, then a horizontal reflection, and then if we have them, a vertical reflection, and then lastly a vertical shift. So you're always kind of working from the inside out, is what I should really say. And then, yeah, so Jesus' question, when we have a negative x under a square root, can we put in a positive number? We cannot. Well, I mean, we could here, we could put in +1, because -1 plus 2 is still a positive number. But in this previous example, we could not put in a positive number for x. We put in 4 for x, then we have the square root of -4. And the square root of -4 is an imaginary number. And we don't graph imaginary numbers, right? If we have a -4 in the square root, we say, oh, it's not defined there. Because again, I know we don't say this usually, but all these functions we're talking about are what are called real valued functions, meaning the y values, the outputs, they have to be real, non-imaginary numbers. So no, we cannot put in a positive value for x here because it'll make the insides negative.
So if we put it like a -2, it'll give us a positive x though, right?
Right. So exactly. So if for example, in this one, if I said x was equal to, right, if x was -2, it would be totally fine. It wouldn't be a nice integer number, but it'll still be a real number. It'll be the square root of -2 plus 3, which is about 4.4.
Okay, thank you.
You're welcome. So back to this one. Here's how we're going to do this one. We're going to take the parent graph of the square root of x. We're going to horizontally shift it which way? 2 to the, good question, 2 which way?
Right?
So this is where things are a little bit extra confusing. It is going to be 2 to the left because so I'm adding on the inside, I know x has to be less than it would have been so that we get the same results, right? So I know that right here, if I plug in 0, I get out 0. Here, if I plug in -2 for x, I get out 0 for y. So I'm shifting to the left like that. But now here's what's going to happen. I'm going to now do the reflection. So I'm going to do y equal to the square root of -x plus 2. I should have written some words in there. One sec, sorry. So here, right, we shifted 2 left. And now here, we're going to reflect horizontally. So, but we're reflecting across the y-axis, meaning we're flipping the thing around here. So this point that's over there, -2, 0, is going to flip over to the other side and be +2, 0. So what it's going to look like is it's going to look like that, right? This thing got flipped around the y-axis. So at the end, it kind of looks like we actually flipped it and then shifted 2 to the right. But I find it confusing to make that work sometimes. So I will say this process of doing it this way will always make sure it comes out correct. Whereas if you try and kind of do the flip first and the shift second, it can kind of come out, it's just less precise, or it's less careful, or it's easier to make a mistake if you do it a different way. So I would really encourage everyone to, if you see a horizontal reflection and a horizontal shift, to do the shift first as we normally would. If you're adding, then we know we shift to the left. If we're subtracting, then we know we shift to the right. And then afterwards, do the horizontal reflection around the y-axis. Yeah, that's all I want to say there. I don't think there are many, if any, questions that actually have both these things in them, but it's something that can come up later, so I thought I should mention it. But so if you are looking at the class notes, it does say there's a note in the class notes on the last page of class J, which is to do any flipping before you do any shifting. And I've written in there in the notes I've written, you want to actually shift horizontally like we did here before you flip horizontally. So horizontal shift, horizontal reflection, vertical shift is the order that we should do these transformations in. And we'll talk about that a little bit more after we do these next two parent functions. So there's 2 more parent functions I want to talk about, because they do come up relatively often. And they are the following. So they are both rational functions. A rational function is just a polynomial divided by another polynomial. This is kind of the most famous one, f of x equal to 1 over x. They're not very exciting polynomials, right? The polynomial of 1, or y equal to 1, is kind of super boring. It's just a constant function, but technically it's still a polynomial. It's a polynomial of degree 0. And y equals x is also a pretty boring polynomial, but it is a polynomial of degree 1. So this is a rational function, and it looks like the following. There's a couple points I think about graphing. I like to graph the point 1, 1, and -1, -1. When x is 1, y is 1. When x is -1, y is -1. And then here's what I think about. Yeah, I'll just take the whole page here. So we don't have to make a table, but I'm going to make a table for a little bit. So if x is 1, y is 1. If x is 2, y is 1/2. And if x is, say, 3, y is 1/3. And if x is, say, 1,000, y is 1 over 1,000. So as the x values get larger and larger and larger, the y values get smaller and smaller and smaller, but still positive. So what we have here is a horizontal asymptote, right? A value that the function gets closer and closer to as x gets larger and larger. So we have a horizontal asymptote of y equal to 0. And that's actually true as x gets really, really positively large and as x gets really, really negatively large. If x is -1,000, which is way out that way, the y value is 1 over -1,000, which is a very, very small negative number. So as we move out to the left, our y values get negatively small. Okay, well, what happens as we move in? What if we get really, really close to 0? Well, if x is, say, 1/2, y is going to be 1 over 1/2, which is 2. So as we move in, we're actually getting a little bit bigger. There's 1/2, there's 2. Or if x was, say, 1/10, y would be 1 over 1/10, which is 10. Or if x was 1 over 1,000, which is still bigger than 0, right? It's a very small positive number. Y is going to be 1 over 1,000, which is 1,000. So as the x values get closer and closer and closer to being 0, the y values get larger and larger and larger. I know we're not talking about limits, but in the language of limits, we would say as x approaches 0, y approaches infinity. And then the same sort of thing is going to happen from this side, except the values are going to be negative, right? If x was a very small negative number, like -1 over 1,000, then the y value would be 1 over -1 over 1,000, which would be -1,000. So as we get closer and closer to 0 from this side, the y values get very, very negative. And so we'd actually say we have a vertical asymptote at x equal to 0. And I would also mention that this function is undefined at x equals to 0. Right? We can't divide by 0. We can see what happens when the x values get really, really close to 0, that the y values get very, very large or very negatively large, but we can't actually divide by 0. And that should say, right, the domain is all real numbers except for 0. And that's actually true for any rational function. For a rational function, the domain is always wherever the denominator is not 0. And then we could also talk about the range, because why not? The range here is all y values except for 0. So everything except for 0, right? This function never equals 0, right? 1 over a number can't ever equal 0. All right, one more, and then we'll move on to class K. one more very similar but slightly different rational function. So the other one I want to graph for you is g of x equal to 1 over x squared. And hopefully, I can pretty easily convince you that we're going to have some of the same features, right? If x is very, very large, the y values are going to be very, very small. Actually, before I even go there, let me start off by plotting the 2 points I want to plot. I always find it useful to plot when x is 1 and when x is negative 1. If we can, right? We can't do negative 1 for square roots, but whatever. If x is 1, 1 over 1 squared is 1. If x is negative 1, 1 over negative 1 squared is 1. In fact, you can see that for this graph, all the y values are going to be positive, because even if x is negative, the negative number squared is still positive. So now as x gets larger, the y values get smaller. If x is 2, y is going to be 1 over 2 squared, which is 1/4, which is pretty small. This one actually gets smaller faster, right? This one, when x was 2, y was 1/2. This other one, when x is 2, y is going to be 1/4. So if the denominator is the bigger thing, the numerator, the whole fraction is going to get smaller faster. And then if x was 1/2, 1/2 squared is 1/4. 1 over 1/4 is 4. So it looks similar, but not exactly the same. And then it's actually going to be the same on the left. A reflection, if you will. So this graph also has a horizontal asymptote of y equal to 0. Also has a vertical asymptote of x equal to 0. It's undefined at x equals to 0. Has a domain. It's everything except for 0. All reals except 0. Has a range. Here the range is less than before. The range is all positive numbers. And those are the pertinent details of this graph. And then we'll talk about doing some shifting and reflecting with these graphs in K, I believe. So that's the end of section J, class J, whatever you want to call it. Are there any questions about these last two graphs before we move on? And we're still going to deal with these graphs, so like we're not done with them, but are there any questions about this one or the previous one before we move on to class K?
About what a horizontal asymptote is?
Say that one more time. Sorry, you broke up a little at the beginning.
Could you just quickly talk about what a horizontal asymptote is?
Totally. And so you'll definitely talk more about this when you take calculus next quarter. But the idea of a horizontal asymptote is just it's a horizontal line, which both of these I can't draw. Why? Because they're already, right? It's already the x-axis, which is y equals 0. But it's a horizontal line that the function is getting closer and closer and closer to as you move away from the center. So here, right, as x gets larger, this is getting very, very close to the horizontal line y equals 0. And as x moves that way, the function gets very, very close to the line y equals 0. Another way to say it is that the y values are getting closer and closer to a specific value, which is y equals 0. Okay. Yeah, and we'll re-encounter this idea when we talk about rational functions more, because there's definitely a whole section, I think it's class P or Q or R, where we talk about rational functions. And then we will talk more about different horizontal asymptotes. But yeah, and I will also say, although these examples, the graph does not cross the horizontal asymptote, it is definitely possible for a function's graph to cross its own horizontal asymptote. We'll certainly see that in the future. Go ahead, whoever was about to ask a question.
Yeah, so I'm just clarifying. So domain refers to all the x values, right? And the range refers to all the y's, like all the possible y's. Okay.
And for this one, the domain and the range are the same, right? The domain is all x values except for x equals 0. The range is all y values except for y equals 0. Whereas I'm going to flip back over if that's okay, Mason. In this one, the domain is all x values except for x equal to 0. But the range is only the positive y values because we don't get any, right? The graph is never below the x-axis. So we never get any y being negative value. But yes, your clarification was exactly correct, Paula.
Thank you.
You are welcome. Okay, so let us talk about class J, which is more graphing, specifically in the context of talking about stretching and compressing. Really, we're kind of putting it all together in one big picture. I will tell you, as far as I'm concerned, and most people are concerned, when it comes to transformations, there are 3 types. We've already talked about 2 of them: reflecting, shifting, and then we have the stretching or compressing, which is the 3rd type. And the 3rd type is kind of the least important type. Being able to shift a graph appropriately or reflect a graph appropriately is kind of the bread and butter of transformations. The stretching is kind of something we're like, yeah, they're stretching, and sometimes it's more important. It is especially important when we talk about trig functions. That is actually the time when the stretching and compressing is kind of the most vital. For other graphs, we kind of take it with a grain of salt. So I'm going to try not to do too much with this because it's not something I'm going to ask you a whole lot about. So the question we have for class K is, how do I not ruin this pen? Trying to make my black pens last longer because they are my favorites. What does multiplying by a number, do to the graph? Of x. And just like before, with the reflecting and the shifting, there's going to be 2 options. There's going to be if we multiply outside of the function and if we multiply inside of the function. So we could have y equal to a number a times f of x, where a is outside, versus, let me use a different color so I can, y equal to f of b times x, where b is inside. And we're gonna consider a and b to be positive numbers because we know that if you have a negative, that's going to give you a reflection. So we're going to kind of keep those separate. So if I had if it was a negative 5 times f of x, I really think of that as a -1, giving me a reflection vertically, and then a 5, which is going to give you either a compression or a stretch. So what's going to happen here is, yeah, sure. So clearly this is outside. It's going to affect the graph vertically. This is going to be a vertical stretch or compression. A stretch meaning, right, it's going to kind of get stretched out. A compression meaning it's going to get squashed down vertically. And here are the 2 rules. So if the number you're multiplying by here is greater than 1, then it's a stretch. And here's why. If you're multiplying by something that's larger than 1, the y values are going to be bigger than they were before. On the other hand, if you're multiplying by something that's between 0 and 1, then it's going to be a compression. Because the y values are going to be smaller than they were before, comparatively. And then, yeah, if there's a negative, we do a vertical flip, which I'm not going to write down because I don't think we really need to. On the other side, so we're going to talk about the other side, and then we'll do an example. I hate when I get pen on my fingers. It's really not my favorite. So if you multiply by something on the inside, you're going to have a horizontal stretch or compression. Now, here is where, again, the counterintuitiveness is going to come into play. So just like with shifting, right? If you shift, when you add a number inside, you have to shift to the left because x has to be smaller to compensate for the number we've added. Or when you subtract on the inside, you have to shift to the right because x has to be larger to compensate for subtracting. Here, if the number you're multiplying by on the inside is bigger than 1, then we're going to get a horizontal compression because the x values are going to have to be smaller to compensate for the fact that they're being multiplied by something like 2 or 3 or 5. So we get a horizontal compression, right? Which is kind of the opposite from the vertical, right? For the verticals, if the thing you're multiplying by is bigger than 1, you get a vertical stretch, and you get lengthened versus squashed. And then likewise, if the thing you're multiplying x by is between 0 and 1, then you're going to get a stretch horizontally. So those are the rules. That's what's happening. Let's look at an example. Yeah. Now, one of the issues with some of these examples is if things are kind of centered around the origin, it can look like a horizontal thing is really a vertical thing and vice versa, which is unfortunately kind of what we're stuck with. So let's look at this example. Let's look at, I want to graph y equal to 3 times the absolute value of x minus 4. And I'm going to do this in 3 parts. So here's the absolute value of x. And we've got points like 1, 1, 2, 2, and negative 1, 1, and so on. And now I'm going to graph the stretch part, the 3 times it. So I'm going to look at y equal to 3 times the absolute value of x. And what's going to happen? Well, the y values are going to be 3 times as large as they would have been. So instead of getting the point 1, 1, well, if x is 1, y is now going to be 3 times 1. Instead of getting the point 2, 2, if x is 2, y is now going to be 3 times 2, which is 6, which I don't think I'm going to actually graph. Instead of getting the point negative 1, 1, I'm going to get the point when x is negative 1, y is going to be 3 again. So you can see I've taken this graph and I've stretched the y values up. In fact, you can even, sorry about it. If you, right, you can kind of think about this point is getting pulled up to something 3 times as big as it is. And this point here is getting pulled up to something 3 times as big as it is. And same deal on the left. That's what's happening when you multiply on the outside by a number that's larger than 1. All the y values get multiplied by that factor, and you get stretched away from the x-axis, which can be up if you're above the x-axis or down if you're below the x-axis. And then finally, we're going to shift it down 4. So our final result here, so I'm going to go, I know the origin is going to go down 4. And then I would probably think, well, this point here, which was 1, 3, that's going to go down 4 as well. So it's going to be 1, negative 1. And there's my graph. Questions about this example?
So this is like on the inside of the function. This is like the -4 is in the inside of the function, not on the outside.
On the outside, right? The 3 is on the outside of each of those. But I will point out, this is again kind of unfortunate, it's very much the same. In fact, it's literally the same. This would be the same as the absolute value of 3x minus 4. So notably, multiplying by 3 on the inside is giving a horizontal compression, which is also an accurate way of thinking about this, right? Instead of thinking about these points getting stretched up this way, you can also think about them getting compressed inwardly like that. And that's unfortunate but true, is that a vertical stretch and a horizontal compression often look the same. But we'll try and differentiate between them. Now, to be perfectly honest, if I was going to graph that thing, I wouldn't really think about the stretching part. I would think, okay, I've got y equal to 3 times the absolute value of x minus 4. I know the parent graph is the absolute value. I know this 3 is going to do some sort of stretch. But what I'm really going to do is I'm going to say, okay, I know it's a V shape. I know that the downward shift of 4 is going to give me this point here. And then I just have to find another point. So I might try and find an intercept. I might say, okay, if y equals 0, then 3 times the absolute value of x equals 4. 4/3 equals the absolute value of x. So x equals plus or minus 4/3. I might do it that way. And not even really think about the fact that there is a vertical stretch going on. If you can find points, you kind of get the stretch or compression without having to do the work of finding it. We're definitely not going to finish this section. That's okay. I might have to modify the homework. I'll think about what I'm going to do, and then I will let you guys know relatively soon. Still got 10 minutes, so we can get through a fair amount of stuff on it. So let us look at the next one, which is I want to graph f of x equal to, f of x equal to the square root of 1/4 x. So multiplying by 1/4 on the inside is going to give me a horizontal stretch. Because again, x needs to be 4 times as large as it would have been. Here's my parent graph table, x square root of x. So, right, our usual values would be 0, 1, 4, 9. Our y values would be square root of 0, square root of 1, square root of 4, square root of 9. But now if I'm doing the stretched graph, where I'm doing x and the square root of 1/4 x, well, I want 1/4 x to be these nice numbers. So x can be 0, but then for us to have a 1 in there, x has to be 4 times as big. So x has to be 4, so that 1/4 of x is 1 and the square root of 1 is 1. And instead of 4 here, x now has to be 16. So that 1/4 times 16 is 4, and the square root of 4 is 2. And then x has to be 4 times 9 is 36. So that 1/4 of 36 is 9, and the square root of 9 is 3. So I really, really, really want everyone to see this. The x values for my horizontally stretched graph, right? My x values have to be 4 times as large to get the same corresponding y values. That's why it's a horizontal stretch, because the x values have to be bigger than they were before. So I'm going to try and graph this somewhat nicely. And I'm going to, so here's my parent graph dashed, so it doesn't get too in the way. And then my stretched graph, so I'm going to the point 0, 0. Typically, if you've got the origin can't really move. Maybe Alessandra, I'm just trying to make it, yeah, I mean, yes, it would make it easier. Is it required? No. You can just kind of stretch it out and see. Typically getting like 1 more point is kind of nice. So I might just get like these points versus these points. So instead of getting the point 1, 1, I'm gonna have the point 4, 1. So 1, 2, 3, 4, up 1. And I'm not good at drawing it, as you can clearly see. But what you can kind of see here is, yeah, look, this value here, this 1, 1 point, is getting stretched to the right. And this 4, 2 point is getting stretched to the right, where the next one would be 16, 2. And then on the other side of it, we could also do a horizontal compression. If I was going to graph g of x equal to the square root of, say, 2x. Now the x values have to be half as big as they would normally be to get the same corresponding y values. So really, I'm thinking I want these y values. To get them, well, to get 0, x has to be 0, because the square root of 0 is 0. To get 1, I need to take the square root of 1. Well, to get the 1 inside, x has to be 1/2. Because 2 times 1/2 is 1, and the square root of 1 is 1. To get 2, well, 2x has to equal 4, because the square root of 4 is 2. So x has to be 2, half as big as it normally would be. And then to get 3, x is going to have to be 9/2, because 2 times 9/2 is 9, and the square root of 9 is 3. So right here, all the x values are going to be smaller. Instead of getting 1, 1, we're going to get 1/2 1, which is like right there. Instead of getting 4, 2, we're going to get 2, 2. And instead of getting 9, 3, we're going to get 9/2 3. So 1, 2, 3, 4.5. 3, sure, it's about right there. So we're taking our parent graph here and we're compressing horizontally backwards. We're scrunching this graph towards the y-axis. So here is the putting it all together part. I don't think this part is super duper important, but it is worthwhile. This will definitely come back up when we get to section like or class like T, where we talk about trig functions and how to graph them. But here is kind of the whole thing. If you have y equal to a times f of b times x plus c plus d. So here's what all this tells us. This is going to be, so the c is going to be a horizontal shift. It's going to be right if c is less than 0, left if c is greater than 0. The b here is going to be a horizontal, what's the word I'm looking for? I guess I have to say stretch or compression. I think the word for either one is dilation. It's a horizontal dilation. I feel like that word is not particularly wonderful. It's a stretch or compression. It's a stretch if your b is between 0 and 1. It's a compression if b is larger than 1. The multiplying by a on the outside affects it vertically. That's going to be a vertical stretch or compression. It's going to be a stretch if a is greater than 1, compression if a is between 0 and 1. All this is definitely in the notes. Right? If this is not super easy to read, which I understand, if it's not, definitely in the notes for class K. And then finally, adding something outside is going to be a vertical shift. It's going to be up if d is positive, down if d is negative. And then lastly, no, I don't want to say that. Yeah. That's all I'll say. Okay, I'm still got a few minutes. Let's do 1 or 2 more examples. Yeah, I'll move over here a second.
It's up if d is greater than 0 and down if d is less than 0. You put greater than in both.
Oh, I did. Sorry. Yeah. Thanks. Sorry about that. And so just more generally, I will say once again, the vertical things usually happen in an intuitive way, right? It makes sense that if you add to the function, the y values get bigger, so we should do that. Or if we subtract, if we're adding a negative, we're subtracting, so it should be down. Whereas the horizontal things can be thought of as being slightly counterintuitive. If you're adding on the inside, you're shifting left. If you're subtracting on the inside, you're shifting right. Okay. So let's do one more example of these. Let's graph f of x equal to, what do I got here? -1 over x minus 4 squared. So the parent graph is the 1 over x squared. So there's our parent. 1 over x squared. The -4 inside, right? Happening before we do things to shift it 4 to the right. So here is shifting 4 to the right. So 1 over x minus 4 squared. So my vertical asymptote that was x equals 0 is going to shift 4 to the right. And be x equal to 4. So now it's going to look like this. And then the negative, just outside the function, is going to flip it over. It's not a negative x. You could write this as -1 over 4 squared. That's going to flip this vertically. So it's going to look like that. This thing just got reflected over the x-axis.